Good afternoon, everybody, and welcome to this professional development workshop on improving your science. I'm one of the co-organizers. My name is Calin-Jageman. I'm the director of the neuroscience program at Dominican University. One of my co-organizers up here is Richard Ball. He's a professor of economics at Haverford College. He's one of the co-founders and currently the co-director of Project TIER. And our other co-organizer is David Malore from the Center for Open Science, but David is not with us today. He had a flight problem. His flight from Europe here was turned back and had an emergency landing. So he's not going to be able to make it in person, but he will deliver his remarks via video, and we'll be taking questions via Twitter. So it's a brave new modern world we're in. I'm keeping the introductions very brief because we really want this workshop to be rich in content and rich in discussion. So for each of the topics, we've just got a brief 25-minute presentation, followed by, there'll be 5 quick minutes of immediate questions for each presentation, and that'll leave us a full 30 minutes for discussion and open it up to hear from you. Now, the 25 minutes to talk about one of these very big topics is not a lot, so it means we won't be comprehensive. So we've agreed to try to aim towards 3 goals. First, to try to just explain the motivation. Why do we think these practices can improve your science? 2, to help convince you that they're going to be less painful or constraining to adopt than you might think. And 3, to help show you the resources and the way forward so that you can feel confident to return to your own labs and to take these on. Now, on the resources end, I want to point out that, as you can see up on the top right, we have an open science page where we've been putting the slides and links and papers and references. There's a tiny URL there in case you don't want to write down 5 AWP4. And the link is also in the abstract, so you can get there. And so we hope that that'll help you get to the next steps. And before we go, there's just a really important caveat that's obvious but important to state, and that is that neuroscience is incredibly diverse. And these practices we think are good practices, but there's no such thing as one size fits all or one way to do good science in neuroscience. So we'll advocate for these approaches, but we also advocate for you to very thoughtfully apply them to your own research context. So let's start with sample size planning. That'll be my piece of this. And my plan is to tell you a little bit about what not to do, to explain some of the foundational issues, to talk about some of the different approaches to sample size planning. It's not just about power. There are actually other ways to do this. To give you some model sample size plans, to help us think about the sticker shock that goes along with doing sample size planning, and then to find some conclusions and some next steps forward. But let's actually start with the motivation. Why should you sample size plan? There's some pragmatic reasons. One is that your funders are beginning to demand it. In 2016, the NIH revised their application review process to foster better rigor and reproducibility, and reviewers are now asked to assess if a project is designed to produce robust and unbiased results. Sample size planning is one of the key techniques for ensuring robust and reliable results. Journals want you to do this too. In 2014, the NIH convened a meeting with different stakeholders to hammer out what are the best ways forward for reporting preclinical research. These eventual principles were endorsed by numerous societies and journals, and one of the key principles is that authors should report how they determine their sample sizes and justify that they're sufficient. So for example, if you want to submit to Nature Neuroscience, you have to complete a reporting checklist, and the very first thing that you need to do is tell them how you determine your sample size. The Journal of Neuroscience recently rolled out new reporting guidelines in March, kind of quietly, and these do include the recommendation that authors should be justifying their sample sizes and report how they determine that their sample sizes are sufficient. Now, these are external mandates, and so we're going to need to respond to them, but there's some very good intrinsic reasons to think about sample sizing as well. One is that it's part of ethical research conduct. For example, the American Statistical Association has ethical guidelines for people who regularly use statistics. That's us. And one of the principles they articulate is that ethical statisticians strive to avoid the excessive and the inadequate numbers of research subjects, because it helps make sure that we don't waste people's time and expose them to unnecessary risk. And the last and the most important thing I can say to you is that sample size planning is truly an essential ingredient for doing good science. Without a sample size plan, it is unlikely that you will just accidentally collect the right amount of data. You could end up collecting too much, and that's problematic because it's wasteful and it's needlessly risky if you have living participants. More likely, though, you could end up with an inadequate sample size. And this is really bad. Inadequate samples are uncertain samples. That means that they don't give us enough information to draw firm conclusions and to conduct fruitful and progressive science. And the scary thing, and I can't emphasize this enough, is that this is true regardless of the p-value that you obtain. Even if your results are statistically significant, you could have an inadequate sample that will likely be misleading and unreplicable. That's strong medicine. And finally, I want to try to make the point that sample size planning isn't just a necessary ingredient to science, it's a catalyst to good science. It is a secret sauce that will help you do better, more amazing work. How? I can't tell you that right away, you'd leave. So you're gonna have to stay for the whole talk, and hopefully we'll come back to that. All right, so we need to work to get an adequate sample size. That sounds simple, but unfortunately, many of the ways that are easiest to do this are also the most problematic. One of the most common ways many life scientists plan a sample size is what we call run and check. You run a batch of participants or animals, you check to see if the results are significant. If they are, you celebrate, but if they're not and they're close, maybe you run a few more. And you check again, and you run a few more. And you repeat this process until you either get what you wanted or you give up. And sometimes run and check is done across generations in a lab. You hand it to one postdoc, didn't work, maybe another grad student tries it later. Now, this is really common, but it is deeply problematic. All the way back in the 50s, Anscombe was warning life scientists not to do this. He called it sampling to a foregone conclusion. The problem is that when you run and check, you are leveraging sampling error. You're giving yourself repeated opportunities to capitalize on chance and find spurious results. This produces biased research results, and it can dramatically increase your false positive rate. So please, if I have one good lesson here, don't use run and check. And you can protect yourself from this by defining a stopping rule, a statement on when you know that you have enough data that isn't defined on looking at the significance value. Pre-registration can help make that commitment public and verifiable, and so David's talk will have a lot more to say about that. Another approach to sample size planning is to use the previously published literature. Our competitor lab had 8 animals per group for this assay. I guess that's what we'll do too. That seems like a good idea, but unfortunately it is not a good idea. It is well documented that neuroscience has a sample size problem. Many of our published studies have sample sizes that are demonstrably inadequate. And I want to explain a little more about what it means to have an inadequate sample size, but for now, what I can say is that if you plan based on what's previously published, you have a very good chance of taking the mistakes of the past and bringing them forward into your research future. So if these common practices are problematic, what do you need to actually do? A good sample size plan has 3 components. It estimates a sample size that's adequate for the research question, it has a stopping rule, and it has some a priori guidance on what will be considered valid data. Sounds easy, right? But what exactly do we mean when we say it's an adequate sample? Now, surprisingly, there are diverse views of this in the world of statistics. Power is what we all hear about the most, but that's not the only way, and some would argue that it's actually one of the worst ways. So I'm hoping to be able to take you through 3 different approaches to power today, though my time will be a little limited. But before we get into them, what you can see is that all of these approaches emphasize thinking about effect sizes. So before we talk about these approaches to sample size planning, what we really have to do is make sure that we're really clear on this foundational issue. So what is an effect size? An effect size is the quantitative answer to your research question. So for example, say that you wanted to know if nucleus accumbens volume relates to drug abuse behavior. Now, usually we frame this in a qualitative way. We just ask, is it or is it not related? We look at a p-value and we make a simple yes-no decision. But in addition to a qualitative approach, we could take a quantitative approach. We can ask, to what degree or extent are these measures related? And for this type of design, the best effect size estimate is your Pearson's R and its confidence interval. We would say that anywhere, based on this data, between 5 to 49% of the variation in one could potentially be related to the other. Now, no matter what your research design, there is a corresponding quantitative question and effect size answer. So for example, here's another example. I pulled all these from recent issues of J Neuroscience. Does knocking out a particular gene help reduce seizures in a mouse model of disease? The qualitative answer we summarize with the p-value. If it's significant, we say yes, it's related. But then we ask the quantitative question, to what degree? To do that, you'd look at your descriptive statistics. The control animals had 10 seizures. The knockout animals had 3 seizures. That's an effect size of 7 seizures reduction, and that has a confidence interval. That's our effect size answer. So effect sizes are pretty simple. They're just the quantitative answer to your research question. And no matter what p-value you obtain, there is somewhere in there in your output an effect size answer and confidence interval that you would really want to look at. Now, it does get a little confusing because even though raw scores are very easy to think about, if we want to compare effect sizes, it can be helpful to look at these in standardized terms. So I want to walk through this briefly. Let's take, for example, in 2016, you take the ACT, the college prep test, and you look at math scores. Men did statistically significantly better than women. That's a qualitative answer. But we could really want to know, how big is the difference? Well, in 2016, the average male score for math was a 21.5, and the average for women was a 20.5. So that's a 1-point difference. Is that a big deal? Well, to answer that, you have to have some expertise. You have to know things about the SAT and mathematical reasoning. I can tell you that the scale for the ACT is a 1 to 36 scale, and the standard deviation is a 5. Now, experts do best when we think about effect sizes just this way, in raw scores that express the data in the terms you're used to using, but it can really help to standardize this so that we can communicate and compare across assays and paradigms. One of the most common ways to standardize is what's called Cohen's d. We just take that effect size of 1 point and we divide it by the standard deviation, which was 5. So that gives us an effect size, a Cohen's d of 0.2, 2/10 of a standard deviation. It's like a z-score for how much the thing matters. There's other ways to do it. R squared is great. For an effect size this great, the R squared is 0.01. That means that no more than 1% of the variation in math scores could possibly be related to gender. We can look at population overlap. The male and female scores would overlap by about 92%. And it can also be really helpful to look at it in terms of sample sizes. If you wanted 80% power to study math differences by gender, you'd have to have about 400 men and 400 women per experiment to reliably detect it. That's a nice way to think about it because it puts it in a resource allocation framework. Now, I've really dwelled on this topic because it's just not possible to really plan a sample size unless you have a strong sense of what effect sizes are and how they work, both in general and especially in your own research field. So let's go down the road of kind of building your effect size sense. Here I've aligned some of the different ways that we can standardize effect sizes, and let's talk a little bit about how to interpret them. Cohen, who was always begged to give these guidelines but said they're not a good idea, famously said a small effect would be about 0.2, medium would be about 0.5, and large would be 0.8. But that was based in psychology, and the results can be really different in your field. And what's really essential is for you to take data from your own field, from previously published papers, and kind of put them on a chart like this to really think through them. Here's how I would do this if I was particularly interested in, say, sex and gender. For example, I might put on the math ACT score. That's about 2/10 of a standard deviation, a very weak effect. If you look in the animal literature, when they look for cognitive differences, like in the water maze, it's a little bit stronger, about half of a standard deviation. Something you need about 50 animals to detect, only accounts for about 7% of the variation. Brain volume is pretty a big difference. If you don't factor out weight or height, just raw brain volume, males and females differ by a full standard deviation. Height's really big. It's 2.2 standard deviations, and that's why it's so noticeable. When you get over 2 standard deviations into 3, you really know the results before SPSS tells you. It's a noticeable perceptual difference. Of course, not everything matters with gender. If you adjust for height and weight, hippocampal volume turns out to be just the same. It's not sexually dimorphic. There are a lot of good guides out there to help you give an idea of what's normal for your field. Sux and Ionides have a range of values that are normal for cognitive neuroscience, but you really have to look. For example, like LTP is an enormous effect. It's 6 or 7 standard deviations or more. It's absolutely qualitative. So it really depends on your field and the assays that you use, and you need to do this to kind of get a sense. It's important not just for sample size planning. It's arguable that effect sizes are the most important thing that you're actually finding out as a scientist. And they're so useful for developing stronger, more quantitative theories, for thinking about practical significance and what you should follow up. And that's why, for example, many journals like J Neuroscience now recommend that you report your effect sizes alongside of those mercurial p-values. So, it's a little bit of a detour, but let's come back to actually start talking about how we plan for power. And again, I want to stress there are multiple views of how to best do this. And I will start with planning for power because it's the most well-known, but I want to hopefully show you that there's some other options, some of which I think are substantially better. Planning for power is really straightforward. First, you define your research question. Then you try to guesstimate the effect size that you think will occur. And finally, you calculate the sample size you would need to be able to regularly detect the effect size of interest. Here's an example. I drew this from J Neuroscience, recent issue. Let's wonder if a particular gene you might be able to knock out would be neuroprotective for induced stroke. You're going to test this by inducing stroke in normal animals and in the knockout animals, and then measuring on the neurological severity score. I didn't know about this before, but it turns out it's a really popular way in animal models to measure how important a stroke has been for animals' motor function. To plan the sample size, you're going to have to guesstimate the effect size. And usually you do this by turning to the published literature. So in a recent paper in JNeurosci, Zhu et al. Found they knocked out a gene called the PRP gene, and they found a large neuroprotective effect of doing this. It was about 1.5 standard deviations. Then you just need to take that effect size and plug it into a sample size calculator, and it'll tell you that you'll need to get 80% power, you're going to need about 8 animals per group. Notice that I plugged in the effect size, the standardized effect size, so you did not have to estimate the standard deviation that I'm going to obtain. It's a common misconception that you have to guess, you have to know all this stuff, means and standard deviations. If you plan in standardized effect sizes, you can plan for power without having to make so many guesses. You just need to guess about the effect you're going to have. But that doesn't mean that this is foolproof. Unfortunately, there's some real problems. The good thing is there's a lot of literature out there on power and a lot of tools to help you. The bad thing is that it can really lead you astray. First, and probably most importantly, planning for power only plans for success. It helps you prove your hypothesis. It doesn't help you have an adequate sample size to disprove your hypothesis, which means you're doing science in a way that can only confirm results and never disconfirm them, which is just institutionalized confirmation bias. Second, the sample size plan is very sensitive to the effect size that you guesstimate. So you really need to do a good job, and unfortunately, that's really tricky. What's published in the literature is often both biased and uncertain. Let's take a look at that stroke study I mentioned. In this study, normal animals had an impairment score of about 12 after the induced stroke. Those that had the gene knocked out had only an 8. That's a statistically significant finding, and it's a very large Cohen's d of 1.5 standard deviations. You'd only need 8 animals per group to study it. But remember, samples aren't perfect readouts of what happens in the world. We should expect sampling error. So let's visualize that uncertainty. Around that effect size, let's put our 95% margin of error. And we should realize that based on this one study, this specific sample, the real truth in the population could be quite different. It could be as large as 3 standard deviations. That's totally plausible and consistent with that data. If that's the real effect size, then our sample size plan of 8 per group is actually wildly wasteful and unnecessarily risky. On the other hand, their data is also totally consistent with an effect size of just 1/4 of a standard deviation. That is an unbelievably subtle effect. To effectively study that type of sample effect size, you'd need about 250 animals per group. Yikes. Now, those are the values at the extremes of the margin of error, and you should take them seriously. But mathematically speaking, those are the 95% worst case scenarios. But unfortunately, even small sampling error can make mincemeat of your sampling plan. Let's say, for example, that Zhu et al. Only slightly overestimated the real effect, that in the population, it's a full standard deviation, which would be very respectable, very important. But you wouldn't know that, so you make your sample size plan based on the 1.55 in the paper, you run 8 animals per group. What's your power if you're only just slightly off? It's just 0.44. That means that you've actually run a bigger sample size than they did, but you're more likely than not to fail in the experiment, even if there's a real big effect there to be observed. Well, that's scary, and it's worth just really thinking about. We often get inconsistent results in our lab, and we might blame them on bad hands, bad reagents, bad grad students. But when you're running inadequate samples, more likely than not, this is just expected sampling variation. It's just what you should expect. The sample that we're trying to base this on is not clear enough to be able to plan a productive set of experiments going forward. And it gets worse, because all I'm looking at there is the uncertainty. We also have to deal with the fact that if it got published, it went through the publication filter, and going through that publication filter increases or inflates sample sizes. Only the strongest survive, and so what we find in the published literature is often larger than reality. So what can you do? Well, one important step is to obtain an operating curve, not to plan for just one effect size, but to look at how your power would deal across a range of possible effect sizes so that you can try to choose more wisely. Another possibility is to hedge your bets, to plan for both uncertainty and the possibility of publication bias. Ken Kelly, who's a statistical hero of mine, he's at Notre Dame, he has an amazing paper that I strongly recommend out this year. And what it is an approach and a method to help you plan sample sizes while dealing with uncertainty and publication bias. It comes with a package for R called Bucks, and it can help you calculate the sample sizes. If you're not an R wizard, he even has a website that you can go to, and you plug in the information you need, and you get the sample size that would hedge for these problems. Here, for example, is the interface for just the simple two-group design. It's very easy to use. I entered the values that I got from the Zhu et al. Paper. I asked for just a very modest correction for uncertainty and sample size bias, and I said that I would like 80% power. And once you plug in just a limited amount of information, Bucks tells you the sample size you'd want to do to really be safe. In this case, 59 animals per group. Yeah, that's not a typo. That's a serious problem. That would be economically infeasible to do. Now, how can that be, right? When you get a result like this and you think, what? I'm not going to do this anymore because that's just crazy. Why? What's happening here? There's two things. First of all, our intuitions about the sample sizes required to do good science are bad. It takes more samples than we normally think. But second, and this is one of the most important things I can say here, the real source of the problem here is the uncertainty of the original result. It is a statistically significant result, that's true, but let's think about it very carefully. The benefit here is about 4 points. That's your signal. But the margin of error is about 3.5 points. That's your noise. This study is statistically significant, but it's very noisy. That's what we mean when we say that a study is underpowered or that it has an inadequate sample size, that the effect you're studying is very close to the level of noise. So it's statistically significant, that's great, but what does that statistical significance mean? It means you can rule out the null hypothesis. It means you know it's not exactly zero. But what can you rule in? Almost anything. Do you know what effect size it is and how you can study it further? It remains very unclear. This result is just too uncertain to be able to plan for the future, to know if it's actually clinically significant, or to be able to replicate. Think about that really carefully. This is a statistically significant effect, but it's not an adequate sample size. You say, oh, I got P is less than 0.05, I can publish it. But what happens next? If you get a result like this and then your lab wants to follow up and say, what's the mechanism? How will you plan the sample size? If you get approached to say, hey, let's start thinking about taking this into the clinical world, how will you assess if this is a blockbuster or actually something of very modest impact that you really shouldn't waste the money following up on? If another lab wants to repeat a result and they run a study like this, yes, they will likely get a result within that margin of error, but much of that margin of error is in the range that they would never have the sample size to do. So the most likely outcome is that they will not replicate you even if you were right, which means your reputation will take a hit. When you publish, even though its point is less than 0.05, it's not enough to build a generative research program on. Significance is not adequacy of sample size. This is one of the things I think is most important about sample size planning, is that it lets us look at our research results with new eyes. It shows us that what we really crave is certainty, not necessarily statistical significance. So that takes me to the next approach, which is planning for precision. Even though I've been delivering a lot of bad news, I think planning for precision is a little bit of sunshine. This approach is called planning for precision. Ken Kelly and some others call it accuracy in parameter estimation, or AIP. And it's really straightforward. You have your research question, and then what you define is how noisy or error prone are you willing to let your results be? What's the level of accuracy or precision that you want? And then you determine the sample size needed to obtain that accuracy. When you plan for precision, it's kind of like choosing the right microscope for the types of cell structures you're studying, or the right amplifier for the type of electrophysiology you're doing. You're planning to get accurate results so that you'll have a strong foundation for future study. So let's stick with our example of our knockout gene and stroke protection. We have the same sample strategy of comparing the control to the knockout genes. And now what we have to ask is, how wrong are we willing to be? We want to compare, to do this, we have to know about the measurement scale. This neurological severity scale goes from a 0 to an 18. So as a scientist, you just have to think about what error level am I willing to live with? The Zhu et al. Paper found a 4-point benefit. So you might think, wow, 4 points, I'd really like to know very precisely what the real truth is. Let's get it down to 1 point. But then your sample size would have to be about 44 per group. Well, how about if I just did the standard 9? Your margin of error would be about 3.3 points. That's pretty hazy, and it means you could easily not detect the effect. Maybe you might settle with something like 21 per group. That gives you a margin error of about 2 points, which is starting to get kind of reasonable. How do you actually make these calculations? There are a number of tools available. Ken Kelly, who I've already mentioned, has a package. He's a leader in this field called MBES for R. It's free and easy to use. It helps you calculate the sample sizes you need to obtain a desired margin of error. His website also has web apps that let you plug in the data and get the sample size you want. I'm showing on the screen here a package called ESCI. It's written by a collaborator of mine, Jeff Cumming. It's an Excel spreadsheet for planning for precision, and it's really easy to do. All you have to do is on the bar down here, drag in the margin of error that you want in Cohen's d terms. The red line shows you the sample size you need to 99% of the time get a margin of error that big or smaller. Now, how do you choose a margin of error? There's no algorithm. It takes thought, it takes having expertise in that field, it takes consideration of the resources you have available. But I can give you 2 rules of thumb. First, if you have a target effect size in mind, then your margin of error should be no more than half as big. That's just good common sense to be able to detect it. Your margin of error should never be more than half as big as the thing you're studying. If you try to do an EFIS and your noise level is 2 millivolts and you're trying to study synaptic potentials, they've got to be at least 4 millivolts, right? Your noise has to be half as big as the signal, preferably better. If you're not sure at all, well, then the goal is to try to find a margin of error that's what we might call theoretically homogeneous, where, whoops, sorry. Oh, I lost it. Where the margin of error will contain values that you don't really care about the difference in. Right? If your margin of error is 3 points, but 3 points isn't a big deal on what you're measuring, that's a great margin of error. Right? There's almost always kind of a region of practical insignificance, they call it, where you want a margin of error where the values in between won't make a big difference in the research decisions that you'll use going forward. The planning for precision approach is my preferred way of planning studies. It's intuitive, even for those who don't love statistics. It works well, even if you don't have clear expectations about effect sizes. And it can also help make your negative data interpretable. In other words, you can prove a negative. You can prove that an effect is close enough to 0 that we could rule it out and not study it any further. It works for frequentists and for Bayesians, which is lovely. And it's also very easy to evaluate post hoc. It's so simple. If you want to know if you have an adequate sample size, look at the effect and look at the margin of error. If they're close to each other, you did not have enough data and you're going to need further study before you really bank on it. Why isn't anybody using this approach? Good question. I think everybody should use this approach. But there is a con, and that's that there aren't quite enough resources. It's not as commonly available to find these tools yet. The ecosystem is growing, though. Now, I knew I was going to be really running long on time, and yep, I've already started to do it. So I'm going to skip ahead towards the end, but I want you to know that all the other slides are available. They're online, so you can page through them if there's more that you want to talk about. But I want to end by talking about the sticker shock that comes along, and it's substantial. Here, for example, is the typical effect sizes we find in the published literature for studying sex differences in cognition in animals. And given those effect sizes, which are probably inflated, to further study that topic would take astronomical numbers of animals. And that's really depressing. So what do? Well, one solution is right in front of us. We need to run larger studies. It makes no sense to do affordable but bad science. And I can't be more clear about this. Science with inadequate sample sizes is bad science. Another painful solution is to give up on some lines of research. Not everything you want to know is tractable, given the resources and the technology currently available. Now, there are some other approaches that can help doing a series of studies or using what's called check-in analysis. I have a good reference here that you can take a look at. But the really important thing is to think about optimization. Science is the art of making the invisible manifest. We magnify cellular structures. We amplify neuronal signals. We detect tiny changes in blood flow to reconstruct the brain's anatomy from outside the body. And that's not just about instrumentation, it's about experimental design as well. We have to do that innovative work to make the small, intractable things that we're interested in into large, tractable effects that we can fruitfully study. Think of all the really productive paradigms in neuroscience, fear conditioning or long-term potentiation. These generative research programs have come from large, reliable effects. Sample size planning helps you realize which paradigms are that way and which aren't, and to start to optimize to try to get your work to be large and reliable effects. That's amazing. I'll give you quickly to end a brief illustration from my own experience. About 8 years ago, I started a project with my collaborator, Irina, to start measuring changes in gene expression after learning in aplesia. The project got funded. We were so happy, but we immediately began to struggle. We weren't finding anything significant. So we went back and tried some genes that were already reported in the literature. And sometimes we got significant results and sometimes we didn't. So we were doing everything. We were ordering new reagents, different animals. We thought our students were bad or we were terrible scientists. It was this terrible year. But I was reading Ioannidis and Cummings and Gelman, and it started opening my eyes. I realized that the effect sizes that had been published were very uncertain. And yet, we were using sample sizes that were standard that just wouldn't be adequate to regularly detect them. And indeed, we weren't regularly detecting them. We were getting results all over the map. But that was normal. That was what we should expect. Now, we were a small lab. We couldn't just do a sample size calculation and order 4 times as many animals. We didn't have the money and we didn't have the time to do it. So what we did is we started optimizing. We switched to a within subject design. We abandoned the type of learning we had been doing and switched to within subjects type of learning because it made the results tremendously more precise. We changed the way we did dissections to reduce noise. We increased the amount of time that we trained the animals to make the effect size bigger. We moved the needle on CREB, a famous transcription factor that's regulated by learning, from 1.5 standard deviations to 2.5 standard deviations. That's an enormous change. And because we were doing it within subjects, we now do overkill of 10 animals per experiment to get really precise results with what we used to get basically crappy results with 16 animals. We're doing better science that we can build off of better with less money and less time and less investment. Optimization is what sample size is all about. It's about resource allocation and trying to figure out the best way to spend your time and effort in animals. And that's the missing ingredient in science that actually makes your science amazing. It's not just a burden or something to jump through a hoop. It will help you be more strategic and do better science. That's the promise. So please do sample sizing. Know that there's multiple ways to do it and that power is not the only way. If you do plan for power, adjust for the fact that there's bias and uncertainty in the published literature. Don't run and check. Don't uncritically accept what's been published as the right sample size. And especially, don't think that just because you're significant, that you're safe. You may have an inadequate sample size that's unreliable and unlikely to replicate, and that will harm your reputation as a scientist. Going forward, I really hope that you will go forward and sample size plan. I know it's not easy. It can be confusing. I've tried to put resources up there. If you find other resources or you're confused, please let me know. Join the Open Science Framework project so that you can crowdsource and we can put our ideas together to make good tutorials to get more people to do this. And you'll be a leader, helping to do more robust and rigorous and fruitful science. And then when you review, when you're on a dissertation committee, when you're talking to colleagues, try to find gentle, helpful ways to lead them where you're going. To let them know that 0.05 does not mean that your sample size is adequate, that run and check is not okay, that they should be reporting their effect sizes, and most importantly, that we should always be looking at those effect sizes and comparing them to the margin of error to see if we've really collected enough data to go forward with that scientific project. I know I went over, I'm sorry, but I want to say thank you to my collaborator, Irina, who helped me so much with it's been a journey of us trying to figure out how to actually do this right. Jeff Cumming, who was a statistical hero of mine, who invited me to be a partner with him. To the many statisticians who've inspired me, SFN for letting us do this thing, and David and Richard for taking a chance to do it. Thank you. Ooh.